vote by committee. And vote by committee, can everyone see that figure on the top? The first one is vote by committee. I know that the vote by committee is not legible from the back, so I wrote them down in the order: vote by committee, collapsing, and proxy. So in vote by committee, what says is, suppose A currently thinks highly of B and C. Okay? But let's say A decides to, instead of directly voting for B and C, A decides to form a committee. And A gives all its vote to the committee. Okay? So A is now voting for everyone in the committee, and everyone in the committee is voting identically to the way A was voting before. Okay? So this happens in academic departments. The department chair wants something to happen. The department chair nominates a committee, goes to each committee member and says exactly how they should vote, and then each committee member comes back with the same thing as the department chair, and then you make a decision. Okay? So that's where the idea comes from, vote by committee. Okay? So, so what this says is, what vote by committee, what this axiom says, is that by doing this, nobody's relative reputation should change. Okay? The relative reputations in G prime, which is a graph, always G is going to be the graph on the left, G prime the graph on the right. The relative reputations of everyone in G and G should be the same as everyone in G prime, except of course nodes which are there only in G or only in G prime, or nodes which are changing between G and G prime. Okay? So the three blank nodes in the middle, I don't know, but everybody else, their relative reputation should remain the same. Okay? And so this is like an example of one kind of transitivity. The other kind of transitivity is collapsing. So imagine there were two nodes A and B which were voting exactly the same way. Then everyone who was voting for A or thought highly of A or thought highly of B, now they directly point to this combined node A, and A is doing exactly what A was doing before. Sorry, let's just say endorsing. Endorsing. So everyone who's endorsing A or endorsing B is now endorsing the single node A, and A's endorsements are the same as A's endorsements before, which were exactly the same as B's endorsements. Okay? Then the relative reputation of anyone who's not A and not B should not change. Okay? A's reputation could change, but anyone else's reputation who's not A and not B should not change relative to each other. Okay? There's a second axiom. The third axiom is proxy, which says that imagine that there are three nodes, and these three nodes have equal reputation currently in G. Okay? And all these three nodes are voting for X, and then X is voting for three other nodes. If you short circuit X, take X out of the picture, and then these three nodes vote directly for the three nodes that X was voting for, 1 to 1, then no one's relative rank should change, except of course X, which went out. Yeah. So these are all different intuitive forms of transitivity, and they all make sense. Okay? So again, instead of writing them formally, I thought we'll just do the picture and see if anyone objects to any of these axioms. You want the pictures bigger? In G, yes. Only in the last one. Yes. And so there are three people who are identical. They're both pointing to X. X is pointing to exactly three people. So numbers have to finally match up, and then you short circuit X. So these are all natural forms of transitivity, and the axioms say that in each of these cases, the reputations in G and G prime should not change, except of course like X has gone out, and in that case A will change because B has gone out, but other nodes should not change. Okay? And so there's a theorem which Altman and Tenenhills prove, okay? And the theorem is that naive page rank naive page rank is the unique reputation system that satisfies A dot 1 to A dot 5. In C, I think that might end up being, you could. So I think the thing with these axioms, because they're labeled transitivity, what you're saying is intuitive. And I think given these 3 axioms, you can derive what you are saying as a sub-axiom. So the question is, why aren't all 3 connected to all 3? So I think the thing with these axioms is that I think both what you are saying and what both of you are saying can be derived as sub-axioms of that. So I think it's more like a matter of taste that they chose to define this as the axiom. Right? So it's not, there's nothing wrong with your intuition except that what you are saying will also follow from these. In fact, it must follow because what you're describing is a property of page rank. And because naive page rank is a unique system that satisfies A dot 1 to A dot 5, any property that naive page rank satisfies is also going to be derivable from these axioms. So unique means that this is the only up to re-ranking. Okay. So yeah, so good. So what's unique? So this is, so if we think of a reputation system as something that's going to give us a total order with ties, that any system that deviates from naive page rank on any graph is not going to be a valid reputation system in A dot 1 to A dot 5. So it cannot deviate, any system that deviates from naive page rank, the ranking that naive page rank produces up to ties on any graph is not going to satisfy A dot 1 to A dot 5, at least one of them. So it's a very strong characterization. And everything here is very non-controversial. It's like very obvious. And the only controversial part is this part. In my opinion, I mean, I haven't really heard anyone object to anything other than this self-edge axiom. Yes? Oh, I see. Okay, thank you. So the question is, why can't there be another algorithm for doing it? And I think maybe there could be another algorithm for computing exactly the same values. But anything that deviates from the ranking that naive page rank produces on any one graph is not going to satisfy these axioms. So if there's another way of obtaining the same rankings, then of course that will also satisfy the axioms. So instead of writing down the naive page rank equations and solving them, maybe you have some other algorithmic way because it's a simple system, so there could be some other algorithm for getting the same rankings. That would also satisfy the axioms. So when I say the unique system, I mean that anything that deviates from the rankings that it produces on any one graph is not going to be valid. With this is the ranking produced, yes. Modular computation method. So once again, in this view of algorithms, you're thinking more of the outputs that it produces than the exact computational method. So, and then there's another axiomatic system which I'm not going to get into, which describes what you would want from a tamper-proof reputation system. And that also, and you can show that these two axioms are not together satisfiable. Yes?
The proof is constructive or it's more we try?
So the proof of this is, so it's an if and only if proof, of course. And so one part of the proof is very easy, and that we can do very easily. And that part of the proof verifies that naive page rank satisfies all these axioms.
Okay, because no, my question was more about
yeah.
if I take all this action,
yeah.
Basically the proof is I construct page rank. Now what I'm talking about constructive proof is basically if I want to add another axiom, because as you said, we are doing a normative approach.
Yeah.
So we can add the other axiom, for example, fairness and so on.
Yeah.
And if it's a constructive proof, perhaps I can construct another kind of page rank.
Yeah. No, the proof is not constructive. So the question was, is the proof constructive? The proof is constructive in the sense that, so first of all, there are two parts to the proof, as you would imagine. The first is to show that naive PageRank satisfies all these axioms, and that's very easy because isomorphism, of course, self-edge, of course, because there's a tie, you add something, you write down the equations, it works out. This is the only tricky one. Okay? And so a lot of people came up to me after the previous lecture and said, why would this axiom be true? And the reason this is true is because PageRank is the unique system which is nicely balanced, okay? Which says that if I point an edge to myself, I'm improving my own reputation. Okay? And if the worry was that suppose V is pointing to V1, why shouldn't V1's rank go up? And the reason is by adding an edge to myself, I'm boosting my own reputation, but I'm also diluting the amount of attention I'm giving to V1, and those two factors cancel each other exactly. So this is the only part where you have to do some work to prove the naive PageRank satisfies it. These things are sort of very, just follow from the equations. Yeah? Now the other part, of course, is to show that no other system can satisfy it. And that part is not constructive. It's a very complex proof. And so unfortunately, because the proof is not constructive, the proof method doesn't really generalize. Altman and Tenenholtz. The question was, who is this proved by? It's Altman and Tenenholtz. And so this proof in my mind like is a marvel in social algorithms in the sense that, of course, the gold standard for anything in this area is Arrow's impossibility theorem, okay, which you're going to see later. But among modern approaches, this is like the gold standard of what an axiomatic approach means, where you could take some important problem like a reputation system, come up with a normative understanding, and what seems to satisfy the normative understanding even actually also satisfies these axioms in an if and only if way. Now, I'm going a little bit slower than I thought, so I'm not going to axiomatize what it means to be a robust reputation system. Yeah? But as you can see, these are reasonable axioms, and PageRank is the only one that satisfies it. PageRank is not robust to tampering or manipulation by self-interested agents, and hence you have some kind of an impossibility result, which says that you cannot have any reasonable robust reputation system. Okay. And that's just a fact of, it's just like the same kind of fact of life as the fact that SAT is NP hard, and that's that. The axiom for robustness is Sybil proofness. So the question is, even if I can't define it formally, can I informally articulate what robustness of reputation is? And the way robustness is typically axiomatized is by defining this thing called Sybils. And a Sybil is basically a copy of, is a fake node that's completely controlled by one person. Think of it as a web farm. I go and obtain a web page, I can control that web page to make it do whatever I want. Okay? And so there's a beautiful proof by Friedman which says that the only reputation system that's robust to Sybils, I cannot affect my own reputation by making many, many copies of myself and making them do whatever I want, is shortest path. Basically, the shortest path from one particular specific node in the graph, let's say some source node, to another thing. But shortest path you can prove does not satisfy these other axioms of reputation, like the ones that I had up there. And so basically, you cannot actually have a robust tamper-proof reputation system. So we have so far focused on reputation systems. A question came up during the break that these are all sort of, PageRank was motivated by search, and this talk is social algorithms. Where does it connect with social networks? Or what is social about this? So I want to now switch gears from doing something formal. Even though we didn't do the proof, this is a formal theorem, right? And to give you a vignette on an application and to show how these things are used. In the process of doing the vignette, I'm going to introduce recommendation systems. I'm going to introduce the common technique for recommendation systems. And then, if time permitting, I'm going to come back and axiomatize recommendation systems and show how, well, not show because I'm not going to give proofs, but describe how the axiomatization is also useful in designing algorithms.
There are other recommendation algorithms, like hits
other reputation.
Right.
So
like hits.
yeah.
So are those also axiomatized in this?
So hits is actually a little bit different. So the question is, there's another algorithm called hits, very famous algorithm by Kleinberg for web ranking. And the question is, how does hits compare to PageRank? So hits was used for web ranking, but it's not really a reputation system. It's more of a recommendation system. And I think the difference between the two is going to become clear very soon. No, hits is not axiomatically well supported, either for reputation systems or recommendation systems. And so what that suggests is that hits is a very useful algorithm for some domains, but for not these kind of recommendation systems where we're thinking of these nodes as individuals who are endorsing people. Yeah. I'm going to revisit hits. Yeah. So please excuse me for like 5 seconds because I'll have to figure out the exact zoom factor for the next part of the talk. So if you go to Twitter, for example, oh, okay, I guess not. Okay. So this slide is not rendering very well, and my Wi-Fi is not working, so I can't show it to you online. Okay? So you'll have to follow along a little bit. So if you go to Twitter, or if you go to Facebook or LinkedIn, and I think also now Pinterest, you will see some kind of a box or some kind of a feature which is basically very similar across all these networks, which is who to follow or who to friend or suggested friends, or like you may also know, some kind of a feature which suggests other people you might follow or become friends with. On Twitter, that feature is called who to follow. It used to be a box on the left. They keep changing their design, so I don't exactly know how it shows up now. And what it does is, based on who you know, it might suggest other people that you might want to follow. Okay? And so this is something that I prototyped. I came up with the algorithms when I was on sabbatical at Twitter, and so I know exactly the algorithms that were there at the beginning. I don't know what they do now. So what's the problem? So the problem there is so the problem is very similar to the problem that I articulated. And today is a great example to illustrate this, because often when you think of recommendation systems or reputation systems, there's a lot of data associated. For example, if you're doing recommendation system on Amazon, you have all these product features. Okay? But on Twitter, you don't really have that much content. I mean, people are making small tweets, I mean, and not that many. I mean, unless you are Trump, right? People don't tweet that much. And there's not that much content in each tweet, so really you really have the follow graph to go by. Okay? And the follow graph is a directed network with a set V of n nodes and a set E of k edges. So it's very much like the graph that we had. It's directed. I might be following you, you might not be following me. And so the key idea is to use the follow graph to determine which recommendation to make for every user. Okay? And so it's a network inference problem. But as you can see, it's very much like the previous problem, except that it's going to be personalized. In a reputation system, you're coming up with a single reputation score for every node. In a recommendation system, you're making different recommendations to everybody. So you can think of a recommendation system as just a personalized reputation system. Does that make sense? And so this is the follow graph. So imagine there are 5 people, right? Sally, Bob, Jen, Kumar, and Alex. And these are the people who are following each other. We're going to make a different graph. We're going to make 2 copies of every node, a consumer copy and a producer copy. And so everyone who follows somebody is going to be part of the consumer side. Everyone who's being followed by somebody is going to be a part of the producer side. And if A is following B, then we'll draw an edge from the consumer copy of A to the producer copy of B. So in this particular case, you're going to make an edge from, because let's focus on Kumar. Kumar is both following somebody and being followed by somebody. So Kumar is both on the consumer side and on the producer side. Because Kumar is following Alex, there's an edge from the consumer copy of Kumar to the producer copy of Alex. And because Jin is following Kumar, there's an edge from the consumer copy of Jin to the producer copy of Kumar. Okay? So starting from the follow graph, we have a consumer-producer graph. The reason for going to this formalism of a consumer-producer graph is now it becomes very much like a standard, another kind of recommendation system problem. We're doing not friend recommendations, but product recommendations. So the left-hand side could be people who watch movies, the right-hand side could be movies. The left-hand side could be people who buy something, the right-hand side could be products on Flipkart. Yeah.
But you said that you only want to use the follow graph and not use meta information about the text or...
Yes, for now. Yeah. So once again, so the question is, we want to use only follow information. And the answer is yes, partially because at least at the time when we were doing it.
But from a psychological point of view, it's not a problem because in Twitter you can just follow so many things that perhaps it means nothing in terms of, it can be really bad in terms of recommendation.
Yeah.
Something so simple to do that.
Yeah, so I mean the question is, does it not lead to bad recommendations?
Yeah.
No, I mean it was surprisingly good. It was quite good. Yeah. People don't, the people who follow indiscriminately, they'll get terrible recommendations. But they are following indiscriminately anyway. And so I think, so that's partially sort of,
Now there's kind of a game when you want to be popular, you follow a lot of people that will follow you back.
yeah,
They receive a notation, they receive some
yeah,
comments and so on.
yeah. So the question is, well, what if you follow a lot of people, they follow you back? This system is quite robust to that, not 100% robust, but quite robust to that. Because the people who are following you back are indiscriminate followers themselves. So whoever is followed by indiscriminate follower doesn't get affected much. Yeah. But what you're saying is at the heart of this question came up about what about hits? And the question that you're asking is at the heart of hits versus random walks. Okay. So PageRank is a random walk, and so I know that this is mostly like a big part of this is like the stochastics community. So in that sense, like you should be happy that these random walk-based methods are much more robust to this kind of tampering. And I'll point that out again. And so the thing that you would like to use for recommendations is what's typically called collaborative filtering. Okay? And you can also come up with a normative approach to this, okay? Which leads to collaborative filtering. And the normative approach is, now that I have consumers and I have producers, okay, you can imagine trying to come up with a similarity measure for all the consumers and a relevance measure for all the producers. So again, this is personalized. So like I said, recommendation system is like a personalized reputation system. So you're personalizing it to a special consumer C. Okay? And so who do you think is the most similar to C? Right? I mean, C herself is the most similar to C. So it seems reasonable to say, to get recommendation of C, we're going to compute a similarity score for all consumers. And similarity, I mean similarity to C, and a relevance score for all producers, again with respect to C. I'm going to start with similarity of C equal to 1. Okay. So what that means is C is the most similar to herself. We're going to think of 1 as the most amount of similarity anyone is going to get. Okay. And that's all we know. And then we'll propagate similarity scores along graph edges to compute relevance scores. And what that says normatively or intuitively is that a producer is relevant to C if the producer is followed by people who are similar to C. Okay. And then we're going to propagate these relevance scores back to the left to compute similarity scores. And what that says normatively or intuitively, that a consumer is similar to C if that consumer follows a lot of producers who are relevant to C. And then this becomes like a clear propagation problem. There are many propagation methods, and a lot of them lead to a linear system of equations. Okay. And so this is where the tie to social networks starts to come in. okay, because we are doing these friend recommendations. Yeah. So there are two extreme collaborative filters, okay, that you could use, and I like to call them love or money. Okay. And so love is where all the similarity score of a consumer X gets transferred to each producer that X follows. Okay. And the same in the reverse direction. Okay. So if I'm following 10 people, all my similarity score gets translated into relevance scores exactly for each of them. Okay. And this turns out to be equivalent to singular value decomposition in the dense graph limit. And this dense graph limit, and in general, not even the dense graph limit, this is also equivalent to hits. This is basically hits. Okay. And you don't need to know the definition of hits because this is the definition of hits, but hits is a very well-known algorithm for ranking and recommendations by Kleinberg. And so the reason I call this love is because if you ask a mom who has 6 children, she'll say that I love all my 6 kids equally, and I love all of them as much as I would have loved them if I had only one child. Yeah? And the next one I call money, and the money is if X follows D producers, then a fraction 1 over D of the similarity score of X gets transferred to each producer that X follows. Okay? And the reason I call it money is even though the mom loves all her 5 kids equally, when she passes away, her inheritance is going to be divided 1/5, 1/5, 1/5. Right? You can't like say, oh, I love everyone, so all my money goes to everybody. Okay. And this is equivalent to another algorithm called SALSA that was suggested also in the context of web ranking. Okay. What does it stand for? Sorry. Sorry? Is stochastic augmenting something. Sorry. It's called SALSA. I just forget what exactly it stands for. So money reduces to a set of simple linear equations. Okay. Hits also reduces a simple set of linear equations. But the only thing that I want you to see here is that, as you can see, that sim of X is sort of at some point you have to normalize, otherwise you keep extending all the way out. And so when you do money, it turns out if you look at relevance, you'll see that relevance looks very much like the PageRank random walk. And in fact, if you take out relevance and you take out similarity and you combine them into one equation, you come up with this very interesting observation that money is the same as personalized PageRank run on the consumer-producer graph. Okay. And I haven't defined personalized PageRank yet. Okay. So let me define personalized PageRank. I'm going to skip like a bunch of things and describe like exactly how this part of the talk connects to the previous part of the talk. So personalized PageRank says that given a consumer C, and now you're given a graph, a directed graph, you perform a random walk on the follow graph, on this directed graph. And this random walk is the same as PageRank in most ways, except that if the random walk is at a node V, then the walk jumps back to node C with probability alpha. Instead of jumping to a uniformly random node, you always go back to home base. And home base is the client for whom you're trying to compute these, you're trying to personalize your recommendations. And otherwise, you do the same thing as PageRank, which is you follow a random edge out of V with probability 1 minus alpha. Okay? And so the personalized PageRank of node Y is the weight of Y in the stationary distribution of this random walk, exactly like PageRank. The only difference is when you jump back, you jump to this specific node C. And so this can also be computed as a system of linear equations. Okay? And the and so this is where we did something empirical. We didn't really, so no matter how much axiomatic or normative understanding you have to ultimately get back to data. So in order to decide what algorithms to run, what we did at Twitter was that among all possible, a recommendation algorithm says among all possible recommended follows, which are going to be accepted if shown. A prediction algorithm says among all possible follows, predict which are going to be created organically if we don't do any recommendations. So what we did was we tested these algorithms as prediction algorithms as opposed to recommendation algorithms, because you can test a prediction algorithm without actually building a recommendation system. And so that's what we call a dark test. We ran various algorithms to predict follows, but we didn't actually display the results. We just observed how many of the top predictions were being followed organically. And as you can see, money was the hands down winner. So money, which so if we looked at the top, if we said which of the top 100 recommendations from our algorithm were being followed by people anyway over the next month, among the top 100, money at 6, which is a very large number for a recommendation system. So among the top 100 that money recommended, 6 of the people followed anyway over the next month. So we looked at, so we computed the results of all the algorithms at the end of a month, say July. Then through the course of August, we looked at people who actively followed people over the next month, who were active in terms of following people. No recommendations were given. Yeah. And then we said among the top 100 that we had predicted, how many were followed organically. So 6 out of the 100 that we predicted by money got followed organically. Now the next best was personalized PageRank, which was 5. The next best was cosine similarity, which I'm going to go back and define a little bit later. So among the top 1,000, how many were followed? So among the top 100, 6 were followed. Among the top 1,000, 18 were followed. So 6 is actually quite high for recommendation systems in case for this kind of an analysis. Sorry? So these are people who, this is what people followed organically. So a typical person doesn't add 100 follows. A typical, so in this experiment, we looked at people who made at least 10 follows over the next month. So if you think of a typical person, they're going to add only maybe 10 or 20 follows over the course of a month. So out of them, 6 are the ones which are among our predictions. In general, in these recommendation systems and reputation systems and so on, in recommendation system, you're typically, a very good follow rate is like 1%. If people follow 1% of the recommendation that you give them, that's generally considered a big success. So the question was, why 6 a good number? Why 6 not a bad number? And so money turns out to be the best, then personalized PageRank, then cosine, which I haven't described yet, and then love. Okay? So in this particular case, basically the intuition is that eigenvalue based methods or things like hits don't do that well in this setting. Okay? And there's been much further work since our empirical results. For example, Kleinberg himself has a paper which explains why hits might not perform as well in recommendation systems. So clearly this is a good victory for random walks, for the PageRank random walk, but money is still good. But the really interesting thing is, the really interesting thing is, so if you remember, I defined also something called a consumer-producer graph. And the really interesting connection is that the personalized PageRank on the consumer-producer graph is the same as salsa or the same as money. So basically, even though it looked like I had 2 different algorithms which were top algorithms, they're basically both the same algorithm. The one that produced best money is personalized PageRank on the consumer-producer graph, which is where I took the graph and I split this into 2. And the second one is personalized PageRank on the original follow graph in Twitter. Okay? And the next one is cosine, which I'm going to get to later. Okay? And so there's clear evidence that these random walk-based methods work very well. Okay? And this is sort of one of the biggest successes for this idea that you're going to have some axiomatic approach which suggests a particular kind of algorithm, and that algorithm also has empirical support and works well in practice. Okay? Are there any questions about this? So strategically, by the way, and these random walk-based methods had a big impact. So they create billions of follows every year for Twitter. more than 1/8, at the time when I made these slides, more than 1/8 of new followers on Twitter were directly via this who to follow module. But there were also follow-on effects where you would follow someone and then as a result discover more people and follow them. And more than 15% of active users were making at least one follow via this module. But as it turns out, this idea of promoting tweets or promoting accounts, which is how Twitter makes money. If you go on Twitter, for those of you who still use Twitter, if you go on Twitter, you'll often see ads which are like promoted tweets. And these tweets are targeted using basically the same algorithms as, or at least they were when I was there, the same algorithms as the ones that I described. So then the same things that were useful for recommendation also turned out to be useful for monetization. So I hope this makes concrete the connection between the reputation system that we are studying in the last lecture and social networks and why I was calling them a social algorithm. Yeah.
You said that you don't use classical bandit algorithm to promote the tweet. You use a PageRank kind of algorithm.
So the question is that do we use bandit algorithms as opposed to PageRank like algorithms for promoted tweets? So I don't know what Twitter does now, but when the system was first launched, which is when I designed it, it was using not PageRank but cosine. It was using the same thing as the who to follow module. So basically when the system was first launched, promoted accounts is the first product that got launched at Twitter, which was making the money. And that product was using exactly the same, it was designed exactly the same way as a recommendation system. It was using cosine as opposed to random walks. And the reason for that is very interesting. I'll describe that when I get to cosine. Sorry? So the question is, can we talk about fake, I mean, we can talk about fake news at any time. I just don't have anything formal to add. So, I mean, I have my opinions. So the question is, can recommendation systems cause fake news? It's a very deep question. And I feel like a lot of academics like us, right, we criticize the media, Facebook, Twitter, everybody. But what we haven't done a very good job of is academics. I'm not answering that question, sorry, I'm answering a different question. But that's something I learned by watching TV. Is that as academics, we haven't really taken a serious, especially as mathematicians. Okay? Academics who are in other disciplines have done it, but people like us who are think more mathematically, haven't done a serious enough job of saying, writing down normatively what it is that we mean by fake news, axiomatizing it, coming up with a set of guidelines, say these recommendation systems follow this, these don't follow it. Facebook, if you follow these recommendation systems, we're going to stand behind you and we're going to fight for you and say you're doing the right thing, and give quotes in newspapers saying you're doing the right thing. So right now what happens is the academics respond to these things critically in the sense of, here's what you're doing was wrong, and they don't refer to it, they don't react to them normatively or axiomatically or affirmatively, saying this is what you should do, which is right. So I think that's sorely missing. And so, in fact, for me, that's the most interesting. In fact, if I were to think of a research program, which if one of you wants to pursue as a result of this talk, I would say don't work on advertising and don't work on recommendations. There are too many PhDs in Silicon Valley and Bangalore already who are trying to make people click on one more ad, and they can they'll be happy. That ecosystem will be happy without you. But if you could, if you're thinking of a research program, that's a research program. Think of normatively what does fake news mean? Can you axiomatize it? Can you come up with recommendation systems? Yeah. Yes? Oh, so the question is, how did I run this? So was the same user, what was the control, what was the treatment? So this was a dark test, so no one got showed any recommendations. So this is just we just saw what they did without any recommendations. So the question was, no, so the question is, does every recommendation system work well for? Oh, yeah, so the question is, So I think the question is basically alluding to the fact that this is not an A/B test. So in this particular case, there was no A/B test, no experiment really. We just observed what people were doing organically, and we showed which recommendation did a better job of predicting what they were going to do. We also ran A/B tests, and the results from A/B tests were similar, except that for running the A/B test, you had to build a recommendation system. And in these companies, building a system is very expensive. Testing an algorithm on data is much easier. So this is what we used to convince to try to build a recommendation system. Once we had a recommendation system in place, we did A/B tests, and the results were sort of very similar. So I am going to answer that question on fake news in one aspect, one specific aspect later on. On that one specific aspect, these algorithms don't do very well. Another kind of approach does slightly better, and I'm going to also point that out. So then, so now that we have this understanding on, now we have this understanding of sort of which algorithms do well, it's worth sort of going and re-examining axiomatically, saying like, is there axiomatic support for these random walk-based methods? Because clearly the random walk-based methods are outperforming everything. Okay? But this context is a little bit different. It's not reputation, it's recommendations. So can we have similar axiomatic support in recommendation systems? So that's going to be my goal in the next 10 minutes. I'm going to go through it very quickly, okay? Because again, we've already seen one kind of axioms in great detail. The next one I want to do it quicker. Like I said, I left my notes at home, so I'll have to refer to the paper as I'm going along. Yes? Yeah. So if in this test, nothing, we just ran it at the end of July and nothing changed, and then we observed at the end of August. In real life, if you follow somebody, then that person is going to become more likely to be recommended to other people. But it's still somewhat tamper-proof, because if you follow hundreds of people, then your vote gets downvoted, because it's basically in the PageRank random walk. If you follow hundreds of people, then each of those follows takes on less importance. So if you follow somebody, it affects that person's popularity, but not in an as extreme a way as hits. Now, the intuition behind why hits didn't do that well in this experiment is perhaps also interesting, since this question got brought up. Okay? And so what happened was that. Yeah. So basically, what hits does is. So his is this algorithm love. So what it does is, it takes all the similarity score of a user, and it propagates it to the right, to everybody that's following. Okay. So let me just do. So I can't describe it formally, but let me describe it with an example. Okay. So let's say everybody here is following everybody there. Okay. And then C is the only one who's following P. Okay. And let's say A is the only one also who's following P. Okay. And let's say we start with 1 here and 0 everywhere else. In the next step, P gets 1. Okay. And let's assume whenever we go on the right, we're going to reweight. We're going to reweight so the sums end up being 1. In the next step, A gets 1. The step after that, all of these guys all get 1, and this guy gets 2. Because you're going to take all the score of C and A and propagate it to everybody. So Q, R, S, they all get 1 from A, and P also gets 1 from A. That's basically hits. In random walk, in PageRank, you would have divided, Q would have gotten 1/3, 1/4, 1/4, 1/4, 1/4. And so you reweight it so they become 2/5, 1/5, 1/5, 1/5. But basically, hits is the same. Think of hits like the PageRank equations, but you're not renormalizing by the out degree. Now, in the next step, what happens is that C gets 2/5 because C is getting score only from P, but A gets 1 because A is getting it from everybody. And then B and D get 3/5 each. And starting from the next iteration, this component of the graph just completely take over. And you will see that C actually becomes less similar to herself, and P, Q, A, B, and D dominate. And so even if you have a small clique like of size 5 or 10, it just concentrates all the mass on that clique. Okay? And as you can imagine on Twitter, there were definitely small cliques. They were not even like bad people. They were just like small communities that would only follow each other or promote each other. Or there's a travel agent who makes 10 websites, 10 accounts, and all 10 of them follow each other without even any malicious intent. We took out obvious spammers. And all the mass would just go there, and the recommendations were very bad. Sorry? Quora, same thing is happening on Quora, is using the same thing. I know the person at Quora, so I should go and talk to them. If they're using hits, they shouldn't be using hits for Quora. They should at least be using some kind of a random walk based method. Okay? Now there's another intuition, at the risk of not getting into the axioms, there's another intuition behind why random walk based methods work better than hits based methods. So like I said, this method called hits, for those of you who either do stochastics or do numerical algebra, again it's a very diverse audience, so there's almost no language that can connect to everybody. It'll be clear that what this is going to do is basically find a singular value decomposition of some form. Like you're like propagating things left and right. This is like you're multiplying the same matrix with itself over and over again. You'll convert to you're going to find that basically convert the eigenvalues, and you'll essentially find the top eigenvalues. That's basically what you'll end up doing in some kind of a singular SVD space. Okay? Now these SVD based methods work very well for low rank matrices. Okay? And the intuition behind why these methods don't work well on social networks, because human beings tend to be sparse in the sense that we are following a small number of people, but we don't tend to be low dimensional. If you look at all the interests that people have and you write them as vectors, they tend to not be low dimensional. So people tend to be very high dimensional, but they tend to be very sparse. So I might be the number of communities that like, for example, every family is like an attribute. Every community, IIT, Powai, Bombay, Mumbai, like people who like bridge, they're all like, there are so many of these communities that in all these interests, human beings tend to be not sparse. Sorry, they tend to be sparse but not low dimensional. And you can actually also formalize that intuition. Whereas random walks are not relying on people being low dimensional, because you're not taking a low rank approximation of the underlying space, which is what SVDs do. So I don't really think I have time to get into axioms. So maybe if it's okay, what I'll do instead is I'll define. Okay, thank you. What I'll do instead of getting in, so should I get in? Okay, then I'll get into axioms. Sorry, thank you. Sorry, what did I do? Take this. I'm sorry, now my computer froze. If it's okay, I don't think I'll be able to finish axioms in the next 10 or 15 minutes. So no, I'll do something else, which is not axioms. I'm going to describe cosine similarity. I'm going to point out why cosine similarity works better for advertising as opposed to personalized things like personalized page rank. And then I'm going to call it a day for today. And tomorrow I'm going to describe efficient approaches to computing some of these algorithms, because even though these are mostly, we have not been talking about the computational difficulty. So tomorrow I'll touch upon the computational difficulty, and then we're going to do a deep dive into one specific kind of sort of reputation network called curated networks. Sorry? Credit networks, yes. So in these, in a collaborative filter, what we were doing was we had a consumer C on this side, okay, and then we had consumers on this side, and we had producers on that side. And then on the left, we were computing similarities. And the right, we're computing relevances. Okay. And then we're propagating them back and forth. But what you can also do is, in a collaborative filter, is you can have some other way of computing similarities, which has nothing to do with propagation. And you can compute similarities on either side. You can either compute producer-producer similarity or consumer-consumer similarity. And then the rest of the filter, you just do one step of the rest of the filter, and then you are done. Does that make sense? So for example, I could use some other method for computing consumer-to-consumer similarities, do one step of propagation from left to right, and stop. I don't have to keep going back and forth, back and forth, back and forth. So any kind of similarity algorithm can be converted into a collaborative filter. And I can do the same thing on the right-hand side. I can compute similarities on the right-hand side. Like I can compute producer similarities. So let's say this is a consumer. This consumer is following these two people. Let's call them X and Y. And I've identified that this person Z is the one who's most similar to X and Y. I can directly say that Z is the most relevant for C. I don't have to always do the back propagation back and forth. Okay? So in that sense, this collaborative filter method is very robust. You can short circuit you can just take any algorithm that you want to compute similarities on any one side, and then use that to run your whole filter. Did that make sense? And then you just do one step and stop. Yeah? Maybe more general, more robust in the sense that, it's extensible.
Okay.
It's extensible. So you can take, sorry, not robust, but extensible. So what you can do is, I mean, it's also robust in some way, but that's not what I meant to say yet. What I meant to say was extensible. Instead of running the filter back and forth, like we were talking about before in hits or in money, you can have a notion of similarity on the consumer side, and just run one step of your filter to get relevances and stop. Or you can have a notion of similarity on the producer side. Look at all the people that C is following. Just find the person who's the most similar to X and Y and make that as a recommendation. So basically, once you have a similarity algorithm, you can think of that as defining a collaborative filter. And cosine similarity is the following method. I'm going to define it for producers. Okay? So given producers A and B, is this sort of visible? I'm going to also say it out because I realize that it's not always visible. Cosine similarity of A and B given two producers A and B is the intersection of follow A and follow B, the size of intersection, where the square root of the product of the size of follow A and follow B. And follow A is the set of people who follow A. Okay. Sorry? Yeah, sorry, thank you. Yeah. So this is the definition of cosine similarity. Once again, follow A and follow B is a set of people who follow A and B. Can someone point out why this is called cosine similarity? Yeah. Yeah. Is a dot product of the two vectors if I instead of thinking of follow A and follow B as a set, I think of them as vectors, long vectors. Like if there are a billion people, this would be like a billion dimensional vector with a 1 in every location for a person who's following A and a 0 otherwise. Then there's the dot product of those two vectors. Or this is a cosine of the angle between those two vectors. It's like, yeah. So you could imagine running an algorithm which says, I'm going to compute the cosine similarity between all pairs of producers, and the recommendation that I'm going to make to a user C is going to be, or the relevance of Z for C is going to be the sum of the cosine similarities of Z with all the people that C follows. Does that make sense? So relevance of Z, okay, and this relevance is always with respect to a consumer. Okay. Sorry? It's personalized to that it's personalized to that consumer C. So relevance of Z to C is maybe a better way of writing it, is the sum over all X such that C follows X. Okay. I know it's not visible, so I'm going to also repeat it just so it becomes easier to follow. I'm going to call it just cosine similarity CS of X comma Z. Okay. So this would be this is also a collaborative filter. It's doing back and forth propagation. It's just doing it one shot. And so this is what I mean by saying we can use cosine similarity as a recommendation system. Okay. And as you saw from the previous Dart test slide, which I don't have now, cosine similarity was not as good as the random walk-based method, but wasn't that much worse. It was reasonable. Okay. But the nice thing about cosine similarity is it's symmetric. The cosine similarity of X and Z is the same as the cosine similarity of Z and X. Okay. And so for advertising, what ends up being relevant is that unlike for recommendations, if you want to use a recommendation system for advertising, you have to be able to go very deep into the recommendation system. So what do I mean by that? Suppose I want to make a recommendation to you. Okay. I can find the thing that's the most relevant to you and just recommend it. If I want to show you an advertisement and I want to use a recommendation system to show you an advertisement, I can only show you from among people who are advertisers. And those might not be the top 5 people relevant to you, the top 10. In fact, the ads that you see are probably not the top thing that you want to see at any given time. It's probably the 1,000th most relevant thing you want to see, the millionth most relevant thing you want to see. So if you're using something like money or personalized PageRank, for every C you'll have to go very, very, very deep into the recommendation system to find an advertiser. Okay. Whereas this approach, you don't really have to go that deep into the recommendation system because you can run it for all advertisers Z. So given an advertiser Z, you can quickly compute the relevance of an advertiser Z for C. So this turns out to be particularly useful for advertising. Just once. In money, yeah. In that one, you would do this propagation many times. Yeah. Whereas in this one, this is In this one, I can compute the relevance of Z without having to go very deep into the recommendation system. For C, I don't even have to know anything about C. When a user comes in, I want to compute the ads to show that user. I just run through all the advertisers, and for that user, I very quickly compute all of these quantities. It's also very easy to update. It's very easy to update, and you just have to sort of you just have to compute this basically for, you don't have to even compute it for all producers. For every popular producer X and every advertiser Z, you can pre-compute this quantity. And so this is where sort of these social algorithms start to mingle a little bit with computational ideas. So you can pre-compute this. For all popular X and all advertisers Z. And this turns out to be a very easy thing to pre-compute, because even if you do it for the top 100,000 or the top million most popular X's, and the top 100,000 and the 100,000 advertisers that you have, is still a manageable calculation, because as you can see, it's a very simple formula. So you can pre-compute it for all large X's, big X's, and all Z, and then when C comes in, a consumer comes in, they come onto Twitter, they log on to Twitter, you can immediately compute the relevances of all advertisers, and you can immediately sort of show them ads. So once again, even though the empirical work was primarily targeted towards recommendations, it helped. I should really stop. It also helped us design. Since we already knew that cosine similarity does well as a recommendation system, we are fairly confident that when we deploy it, it's also going to do well. It's computationally tractable. It's going to do very well as an advertising system. And the system made Twitter a lot of money and helped them go public. So yeah, so I'm going to stop here. Thank you.